Hello and welcome to lecture 25 of analog integrated circuit design. In the previous lecture, we looked at the random noise in a resistor which happens due to random thermal motion of charge carriers. So, in addition to the current that is predicted by Ohm's law, we will have some noise. It can be represented as an equivalent noise current across the resistor or an equivalent noise voltage in series with the resistor. Now, both of these will be described by their noise spectral densities, and in case of resistor's thermal noise, the noise spectral density is white, that means it has a constant magnitude at all frequencies and it is proportional to the absolute temperature. The voltage noise spectral density is 4 kT times R volt square per hertz, and the current noise spectral density is 4 kT divided by R ampere square per hertz. The two are equivalent descriptions and either one can be used in any circuit for calculating the effect of resistor's noise. Now, the noise is a random phenomenon and it can be described by quantities such as the mean square value or the root mean square value, and to do that there has to be some band limiting since the resistor's noise is wide and uniform over all frequencies. Within some bandwidth, the variance or the mean square value is given by the integration of the spectral density over that bandwidth. Okay. So, the spectral density is nothing but if you pass the noise through an ideal 1 hertz band pass filter, the variance will be equal to the value of the spectral density at that frequency. Okay. We also elaborated this by calculating the spectral density and the integrated noise in an RC filter. If you have a capacitor across a resistor, it will lead to a finite mean square value of noise, and that is equal to kT by C, which is a fundamental result that appears repeatedly in circuit design. Okay. And as I mentioned in the previous lecture, the Mosfet also has noise just like a resistor's noise, and that is what we are going to take up in today's lecture. In today's lecture, we will deal with the noise of the MOS transistor. When we have a MOS transistor, either an NMOS transistor or a PMOS transistor, we have a current that is related to VGS and VDS, and in case of a PMOS transistor, VSG and VSD. Okay. Now, the basic model that we have assumes that ID is related by square law to the VGS, but even if the law is more complicated, there is some formula that gives you the current based on VGS and VDS. Okay. Now, what does it mean to have noise in a MOS transistor? The drain current will be ID, which is the function of VGS and VDS as calculated from the formula, plus some noise. Okay. That is just like we had in a resistor, current predicted by Ohm's law plus some noise. Here we have current predicted by square law plus some noise, and as with the resistor, we will describe the spectral density of this noise, and from that spectral density we can calculate mean square value of noise in different circuits and so on. Okay. So, I will take the NMOS example. So, as usual, we represent the noise by assuming that there is a noiseless transistor which gives you the current predicted by the formula plus some noise IN. Okay. And here we have the current predicted by the formula plus the noise current. Okay. Now, what does the spectral density of the noise current look like? The transistor, as you know, operates in different regions of operation, in the linear region or the triode region and in the saturation region. Okay. Now, it is easiest first to think of what happens in the triode region. Let us imagine that the transistor is operating with a certain VGS and with VDS equal to 0. Okay. That means to say it is operating symmetrically, and if we look at the picture of the device, Under these conditions, there will be a uniform channel going from the drain to the source. Okay. This is the gate, and we of course have the substrate which is connected to some potential. The mechanism of conduction in a Mosfet is exactly same as the mechanism in a resistor. It is due to drift of carriers. Okay. And when VDS equal to 0, the Mosfet is simply a resistor. Now, the charge carriers are due to the channel that is formed by inversion, but the operation is very similar to that of a resistor. Okay. So, it turns out that the noise is also exactly the same as what we would have in a resistor. Okay. In the deep triode region, the transistor is nothing but a conductance which I will call GMOS, okay. And the conductance itself is given by the equation in the triode region, which is mu Cox W by L VGS minus VT. The conductance happens to be controllable by VGS, but it is a conductance nonetheless. Okay. Now, if we had a resistance whose conductance was GMOS, the noise spectral density would have been 4 kT times GMOS. This would be the noise spectral density of the current, okay, the current noise. IN. Now, it turns out this formula is exactly true for the Mosfet in the triode region. Okay. It is 4 kT times GMOS, where GMOS is the conductance at VDS equal to 0. Okay. That is mu Cox W by L VGS minus VT. Okay. In the saturation region, the noise turns out to be 8/3 kT times Gm, okay, at the operating point, whatever operating point the transistor is at. Okay. Just like all the small signal parameters of a transistor depend on the operating point, the noise also depends on the operating point, and it happens to be 8/3 kT times Gm, and you can quickly verify that the current noise in the triode region or the current noise of a resistor is given by some formula which looks like kT times a conductance, and here it happens to be kT times some transconductance. Okay. And if you assume that the transistor obeys square law, Gm is given by mu Cox W by L VGS minus VT. Okay. And from this expression and that expression, you can see that the noise formula is in fact quite similar in the triode region and the saturation region. Okay. The dependence on VGS minus VT is similar, except that we have an extra factor of 2/3 in the saturation region. Okay. In fact, the noise of the Mosfet turns out to be given by this particular formula, 4 kT times the magnitude of the charge in the inversion layer divided by L square. Okay. This is true in all regions. Now, we know that from the formula for CGS in the triode region and the saturation region, when the transistor is operating in deep triode region, the total charge is given by Cox WL VGS minus VT. Okay. And when the transistor is operating in saturation region, the charge in the channel is given by 2/3 Cox WL VGS minus VT. Okay. So, this formula covers both the triode region and the saturation region and all the regions in between. Okay. The transition as usual is never discontinuous, but it is continuous. If you manage to find the charge, a formula for the charge in all the regions, you can use this formula to accurately predict the noise spectral density. Now, for hand calculations, we assume that it is either in the deep triode region or in the saturation region, and use these formulas, okay, the two formulas that I have written down here, and most of the time in amplifiers we will operate in the saturation region, and this is the formula that we use. Okay. The spectral density SID, it is white. Okay. The noise in a Mosfet is also due to thermal fluctuations of carriers. Okay. This is the thermal noise of the Mosfet, just like we had the thermal noise of the resistor, and that happens to be white with a spectral density equal to 8/3 kT times Gm in the saturation region. Okay. Now, how do we use this in any circuit? In parallel with every Mosfet, in parallel with every MOS transistor, we will add a current source representing the noise of that MOS transistor. Okay. And the spectral density of this is given by that expression. Okay. Now, if you have a circuit with a number of MOS transistors and you have a certain output voltage, let us say V naught, you find the transfer function from every noise current source to the output, okay, and you will have the output to be a superposition of all these noise current sources. Okay. And because the noise from different devices are uncorrelated from each other, the output will be simply the noise spectral density of first source times the transfer function magnitude square plus noise spectral density of the second source times the transfer function magnitude square, and so on. Okay. Exactly what we did with resistors. So, if you have a number of components including resistors, you have to do this for every noise source from every Mosfet and every resistor. Okay. We will soon see an example of how to do these noise calculations when we have Mosfets and resistors. Okay. Now, it turns out that in addition to thermal noise, there is also flicker noise in a MOS transistor, and this flicker noise happens to have a different spectral density. Okay. Now, like thermal noise is caused by random fluctuations in the motion of charges due to some non-zero temperature, flicker noise is caused by a completely different reason. When you have a MOS transistor, the charge in the inversion layer is what is available for conduction, and the charge in the inversion layer equals the charge on the gate. Okay. That is assuming there are no fixed charges in the dielectric. It turns out that at the interface of the dielectric and the semiconductor, there are trapped charges, and these trapped charges are randomly trapped and released with differing time constants. Okay. There are different theories about flicker noise. One of the theories is that the charges are trapped and detrapped with different time constants, and the sum of all those things gives you some noise which is flicker noise. Okay. Because the amount of charge in the inversion layer is balanced by the charge on the gate and also all the fixed charges that we might have in between the two plates, we will have some randomness in the number of charges and consequently a randomness in the current as well, and this phenomenon is known as flicker noise. Okay. Now, the flicker noise as thermal noise is described by some spectral density. Okay. We can think of the MOS transistor as having thermal noise and also additionally a flicker noise. Okay. In practice, of course, we represented by a single source which represents the sum of these two noise currents. Okay. Now, it turns out that the flicker noise is related to some constant, some proportionality constant, and the operating point current divided by L square, and also the spectral density is not constant with frequency. Okay. This is an important distinction between white noise and flicker noise. White noise spectral density is constant with frequency, whereas the flicker noise density is not constant with frequency, it is inversely proportional to the frequency. Okay. So, the sum of thermal noise and flicker noise will be the total noise of a MOSFET. Now, as you can expect, this flicker noise spectral density increases when the frequencies are low, because of the inverse proportionality to frequency. So, it is particularly troublesome in low frequency circuits. Okay. So, the MOSFET, if I plot the total power spectral density, total spectral density of the noise current, what I will have is the thermal noise part, okay, which depends on the operating point as 8/3 kT gm, and the flicker noise part, which I will represent it as a straight line. It is inversely proportional to frequency, but I have assumed that the spectral density is plotted on a log scale and the frequency is also on a log scale. Okay. So, this is the flicker noise part of it, it is like that. At low frequencies, the flicker noise spectral density will be more than the thermal noise spectral density, and at high frequency the thermal noise spectral density will dominate. The frequency at which the two spectral densities are equal to each other is usually denoted by f1 over f, the flicker noise corner frequency. Okay. So, the total noise spectral density will be the sum of the two, and it will look something like that. So, if you are making a low frequency circuit, you are probably going to be limited by flicker noise, and if you have a high frequency circuit, you are probably going to be limited by thermal noise. Now, one other difference between thermal noise and flicker noise is that thermal noise is a more fundamental phenomenon. As you can see, it is just related to the absolute temperature and the fact that you have some current flowing through it. Okay. When you have some transconductance, you will have some thermal noise, and even in the triode region, you will have some thermal noise. Now, flicker noise, it is related to these interface traps, and consequently also related to how clean the fabrication is and so on. Okay. Now, if you take two MOSFETs, let us say from two different vendors, and bias them at the same transconductance, they will have the same thermal noise in saturation region, but they can have very widely different flicker noise spectral densities. Okay. Because that depends very much on the fabrication process that is used and so on. That is why we also need that empirical constant k in the formula for the flicker noise. Okay. So, it is entirely possible that if you take similar processes, let us say 0.18 micron process from foundry 1 and foundry 2, one of them has much less flicker noise than the other one. Okay. And that may also influence your selection of process, especially when you are operating at low frequencies. Okay. So, here when I say low and high frequencies, I mean whether it is lower than the flicker noise corner frequency or higher than the flicker noise corner frequency. Now, the flicker noise corner frequency again is not some hard and fast number, depending on the process, it can be high or low, meaning it could be in the hundreds of kilohertz range if you take a long channel technology like 0.5 micron or so, and in the really deep submicron processes which are very common today, the flicker noise corner frequency could be many hundreds of megahertz as well. Okay. So, but once you have the process information, you will be given the flicker noise information, and you have to design your circuit so that the total effect of flicker and thermal noises are sufficiently small, so that your circuit operates without being affected by noise. Okay. Now, just one more remark on flicker noise. As I said, the autocorrelation function is the inverse Fourier transform of the spectral density. Okay. And the mean square value or the variance is the integral of the spectral density from 0 to infinity. Okay. Now, if you integrate flicker noise from 0 to infinity, you will also get infinity. Okay. Now, this is a fundamental problem with the theory itself. It is not clear what happens to flicker noise at very, very low frequencies. So, you have to impose some lower limit on the limit of integration. Okay. You integrate not from 0 to infinity like you do based on the definition of variance, but you have to impose some lower limit based on how long a time period you will be observing the noise. Okay. Now, the noise of a PMOS transistor is exactly same as the noise of the NMOS transistor. It will be given by the conductance in the triode region and the transconductance in the saturation region. and just like with NMOS transistors, you simply add a current source in parallel with the PMOS transistor and model it, and when you have many transistors you have to add up the effects of all of them. Okay. You know, PMOS and NMOS transistors have the same small signal model, and all amplifiers can be realized either with NMOS or PMOS transistors. Okay. There are many criteria for choosing either PMOS or NMOS, and one primary thing is the mobility. Generally the mobility of NMOS transistors is higher, so they tend to be used for higher speed applications and so on. But one more parameter which may influence your choice of PMOS or NMOS transistor is the flicker noise. As I said earlier, the thermal noise is fundamental, and an NMOS transistor and PMOS transistor biased at the same transconductance will have the same thermal noise, but they can have very different flicker noises even in the same process. So, if you are particularly worried about flicker noise, you could choose PMOS instead of NMOS or vice versa, depending on the flicker noise in your process. Okay. Now, let us look at an example of noise calculation in a common source amplifier. This is a very simple circuit which you would be familiar with from basic electronics courses, and what is it? And in its simplest form, it has only a transistor M1 and a resistor R. Okay. Now, in reality you will have biasing arrangements and so on. I will just assume that it is biased at some VGS, so that a certain quiescent current ID flows through the MOS transistor, and I add my small signal input Vi to that point. Okay. Now, we know that the output quiescent value will be VDD minus ID times R, and in addition to that you have the effect of the small signal input, and that will be minus GMR times Vi. Okay. We know that the gain of the common source amplifier is GMR, and that times Vi will be the output. Okay. And GM of course is calculated at the operating point of ID or VGS minus VT. I could represent it for instance as mu Cox W by L, the quiescent value of VGS minus the threshold voltage. Okay. Now, I would like to calculate the noise in this circuit. I will assume that there is a certain capacitance C at the output of the amplifier. Now, I introduce this because first of all, in any real amplifier you will have some capacitance, if not an intentional load, at least the parasitic capacitance. And also, as we saw earlier, to be able to calculate the mean square value or the variance, we should have a finite bandwidth. Okay. If you integrate thermal noise or white noise over an infinite bandwidth, you will get infinity, which is a meaningless result. In reality, there will be always some band limiting, and I will assume that it will come in the form of a capacitance C at the output of the amplifier. Okay. Now, I am interested in calculating only the noise. We already know what happens to the signal, it gets amplified by a factor minus GMR. In addition to that, we will have noise, and to calculate only the noise, as usual what I do is I will assume that the input signal is 0. Okay. I will set Vi to be 0. I will use the small signal model of the MOS transistor. This is Gm times VGS, but since my VGS is 0, this will be just an open circuit, and I will assume that there is no GDS. Okay. We know that there is a small signal output conductance. Just for simplicity of calculations, I will assume no GDS, but even if you want to include it, it is very easy. It can be combined in parallel with the load resistance R. Okay. And I have my resistance R going to a small signal ground here, and I have the load capacitance C, and most importantly I have the noise of the Mosfet, okay, and I have the noise of the resistor, and in this case I choose to represent both by current sources. Okay. And what I want to find out is the output V naught due to noise. Okay. How do I do this? All I have to do is to find out the transfer function from INR to the noise and IN MOS to the noise. Okay. Now, the polarity of these noise sources do not matter, they have random quantities. So, I just show it as having some polarity. Okay. Now, you can see that the noise of the resistor and the noise of the MOSFET are in parallel. So, they simply add up with the right polarity. So, the output VO is nothing but in the Laplace domain the MOS transistor's noise plus the resistor's noise times the impedance. Okay. Remember, this controlled current source is inactive because VGS is 0. Okay. So, all we have is a pair of current sources going into a parallel combination of RC, and we also know that the impedance of the parallel combination of RC is R by 1 plus SCR. Okay. Now, we just have to express this in terms of F, that will give us the spectral density, and we can integrate that to get the mean square value of the variance. Okay. So, the spectral density is nothing but the spectral densities add up because these two are uncorrelated quantities, and when we add them up the result is simply the sum of the spectral densities. Okay. By the way, with these polarities this should be a minus, it is not plus. Okay. But that does not make any difference because once they are uncorrelated we simply add up the spectral densities times 1 by 1 plus 4 pi square f square c square r square. Okay. So, this is what we will have. Now, what is the noise spectral density of the resistor? 4 kT by R, that is the spectral density of resistor's noise current plus the noise spectral density of the MOS transistor 8/3 kT gm, plus I could also include flicker noise. Okay. And the whole thing multiplied by 1 by 1 plus 4 pi square f square c square r square. This is the spectral density of the output noise. Okay. What will it look like? The resistor's noise will have some value, the MOS transistor's thermal noise will have some value, and the MOS transistor's flicker noise will have some value like that. Okay. It is assumed that this is the noise spectral density of the current versus frequency both on a log scale. Okay. So, and the total would be something like that, right, and that has to be multiplied by this particular function, and this function will have a shape which starts from r square at low frequencies and then it goes off like that. Okay. So, we have to sum these spectral densities and multiply it by that to get the output spectral density, and it will have some shape of this sort. Okay. It will have some shape like that depending on where this bandwidth of the this particular function is compared to the flicker noise frequency and so on. Okay. So, we can calculate the spectral density. Now, I will calculate the integrated noise or the variance. The variance or mean square value is also called the integrated noise, and just for simplicity I will ignore the flicker noise. Okay. I will approximate the noise spectral density by considering only the thermal noise part of it. Okay. And in fact, I can take the this number out and this is the expression I will be left with. Now, we know that this number comes from the MOS transistor and that number comes from the resistor. Okay. So, what do you think of the relative contributions of the MOS transistor and the resistor to the noise? We will see this also with the integrated noise, but what do you think is the relative contribution? Now, we see that the contribution of MOS has a number 1, okay, multiplied by some 8/3 kTgm, and the contribution of the resistor has 3/2 divided by GMR. Okay. Now, given that this is an amplifier, we expect that GMR is a number that is significantly higher than 1. Okay. Now, it could also be some modest number like 2, but if you do have a high gain amplifier where GMR is much more than 1, it is very easy to see that most of the noise is contributed by the MOS transistor and not by the resistor. Okay. We will interpret this even more later, but it is very obvious from the formula. Okay. Now, to get the mean square noise, I have to integrate SV naught from 0 to infinite frequency, and that will give me okay. So, that is what the result is going to be. Okay. And we will have some expression of this sort. It has Kd by C multiplied by GMR, which happens to be the gain, and then inside this we have the contribution due to the MOS transistor and the contribution due to the resistor. Okay. Now, one quick sanity check is that we assume that the MOS transistor is not there. Okay. Then this will reduce to the RC circuit that we analyzed yesterday, and so we will be left with Kt by C. Okay. Here also we can see that if we take only the second term in the parenthesis, we will be left with Kt by C. So, at least it passes the sanity check. Okay. Now, the actual output noise turns out to be Kt by C times some number that is related to the gain of the amplifier. Okay. This is again a general property. If you try to make large gains at the output, you will also see large amounts of noise. Okay. And also, as I mentioned earlier, the contribution due to the Mosfet is much more than the contribution due to the resistor. Okay. Now, this again turns out to be generally true in any circuit. Let us say we have a chain of amplifiers with the gains more than 1. Now, let us say each one contributes some noise. Now, you expect that the noise from the first stage will matter most, and noise from the next stage matters less, and the noise from the next stage matters even less. Earlier I said that we can model the noise of a MOS transistor using a current source in parallel. Okay. And the spectral density of the current source is given by 8/3 kT gm. Okay. And the same thing can be equivalently modeled by a voltage source Vn, and the spectral density of the voltage source is given by 8/3 kT divided by Gm. Okay. So, these are just two equivalent ways of specifying the same noise. The noise in a MOS transistor, we have 8/3 kT Gm as the noise current, or 8/3 kT divided by Gm as the noise voltage. Okay. Now, the model that we use for the transistor's noise is a MOS transistor with a current source in parallel. Okay. Now, this adds to the drain current. Okay. Now, in the small signal case, we have the current source Gm times Vgs. There are also the conductance and the current source Gmb times Vbs, but I will ignore those things for now. In addition to the current contributed by the controlled current source, I have the noise current In. Okay. So, the total current here is Gm times Vgs plus In, right. Now, I can think of this as not a change in the current, but a change in Vgs. Okay. Now, let us say I have a noise in series with the gate source. Okay. Let us just assume that this is the case and there is no noise in parallel with the drain source. In that case, let us say I apply some Vgs here, and what appears between these two, the gate and source of the actual transistor, is Vgs plus Vn. Okay. I am assuming that this is the drain, this is the gate, and that is the source. Okay. So, what will be the current here? It will be Gm times Vgs plus Gm times Vn. Okay. Now, this noise current here can be equivalently represented by Gm times Vn if the two are the same. Okay. So, the same noise, the noise of a MOS transistor, can be represented by a noise in parallel with the MOSFET or a noise Vn in series with the gate of the MOSFET, as long as the two are related by this expression. Okay. Now, recall that for a resistor we represented it either by a current source in parallel with the resistor or a voltage source in series with the resistor, and the two are related by the resistance value R. In this case, the two are related by the transconductance value Gm. Okay. So, the noise of the MOS transistor can very well be represented by an input noise source, something like that. Okay. And the spectral density of this, given that Vn is related to In by In divided by Gm, the spectral density of Vn will be the spectral density of In divided by Gm squared. Again, the spectral densities are related to squared voltages and currents. So, this will turn out to be 8 by 3 kT divided by Gm. Okay. So, just to make the association clear, the MOS transistor's current noise has a spectral density 8/3 kT Gm, and the voltage noise in series with the gate has a spectral density 8/3 kT divided by Gm. Now, to compare this to a resistor, the resistor's current noise has a spectral density 4 kT times the conductance, which is 4 kT divided by R, okay, and the voltage noise will be 4 kT times 1 over G, which of course is 4 kT times R. Okay. Now, you can see that the expressions are analogous. The only difference is that the MOS transistor has 3 terminals. So, the current noise is a current source that appears between the drain and source. The voltage noise is something that appears in series with the gate, so that it adds to the Vgs of the MOS transistor. Okay. Now, this description is many times very convenient. We will see exactly why. The reason is that we apply an input to the gate source. Okay. Now, most of the times what we are interested in doing is comparing the amount of noise to the amount of signal that we have. Now, in this case, Vgs is the signal. Now, let us say I modeled the noise of the MOS transistor using a current source. Now, to compare the signal with noise, what I would have to do is to calculate the signal that appears in the MOS transistor due to Vgs, that happens to be Gm times Vgs, and compare that to In. Okay. When I say compare it to In, compare it with some metric of In such as its mean square value. Okay. Now, in this case it is quite simple, but it is even simpler if let us say the noise is represented not by In, but by a series voltage source Vn. Okay. So, since Vn simply gets added to Vgs, by comparing the magnitude, some metric of Vn to the size of Vgs, which could be amplitude or root mean square value, I can say something about the signal to noise ratio. Okay. So, referring all the noise to the gate side makes it possible to have easy comparison with the input which is VGS for a MOS transistor. Okay. In a single MOS transistor it is very simple, and whether the noise is represented by current source or voltage source, we can do the calculations easily, but this concept can be extended to more complicated circuits. Okay. Now, let us say I take the same circuit again, right, and this time I will not use the capacitor. So, because of that the noise will not be band limited. So, I cannot calculate the variance, but I will be satisfied with calculating only the spectral density. Okay. So, let me just do that. This can be thought of as another practice calculation in noise. Okay. And I want to find the spectral density of V naught. So, what do? I will again consider a case where VGS is 0, because I calculate the noise without the input signal. I have GM VGS, but this is inactive. Okay. Now, in addition to that, we have a noise current IN due to the MOS transistor and a noise current IN due to the resistor. Okay. INR, and this is IN MOS. Now, previously the sum of these two INR minus IN MOS was flowing through the parallel combination of RC. Now, they will flow only through the resistor. Okay. So, the output voltage here is nothing but INR minus IN MOS times R. So, the spectral density is nothing but SINR plus SIN MOS. As I said, these are uncorrelated quantities and the spectral density simply add up times R square, okay, which gives me 4 kT by R plus 8/3 kT GM times R square. Okay. So, that is the spectral density of the output noise. Now, let us say I have an amplifier with a number of devices, and I can calculate the noise from each device to the output and finally calculate the output noise, right. Now, there is an alternative representation of noise that is many times useful. Okay. So, let us say I have a noisy circuit with a number of components. There could be a number of resistors and Mosfets and also capacitors and inductors, which do not create noise, but influence the noise spectral density. Now, with let us say with 0 input, I calculate the output noise. Okay. I can take a noiseless version of the same circuit. Okay. I apply some input Vn in, and Vn in is such that the output of this noiseless circuit is Vn out. Okay. This is the input voltage that will give you the same noise as the actual circuit when applied at the input. Now, this is not a voltage that will exist in the circuit, this is something that is used for calculational convenience, and this is known as the input referred noise. Okay. This Vn is known as the input referred noise, and the way to calculate it is, first you calculate the output, that is you have to calculate the transfer function from the noise of each of these components to the output, that will give you the output noise voltage. and you divide that by the transfer function between the input and the output, whatever you identify as the input of the circuit. Okay. Now, that will give you the input referred noise, and you can calculate the input noise spectral density by summing up the spectral densities just like we do for any other calculation. Okay. Now, the reason that this is convenient is, let us say we apply an input voltage source as a signal. Okay. We can immediately compare that with the input referred noise and see whether the signal to noise ratio is sufficient or not. Okay. As I mentioned earlier, the input referred noise is not a noise voltage that exists in the circuit. It is an equivalent source that will give you the same output in a noiseless circuit as the actual noise in a noisy circuit, the real circuit. Okay. So, we will do this calculation for our example. We know that the output noise spectral density is 4 kT by R plus 8/3 kT gm times R square. Okay. This is of course calculated from the small signal model, but I will just show it here. Now, we also know that the transfer function from this point to that point is the gain of the common source amplifier. Okay. From Vi to Vo, the gain is minus Gm R. Okay. Vo is minus Gm R times Vi. Okay. So, that means that the output noise, the actual output noise is related to the input referred noise by minus Gm R times Vn in, where Vn in is the input referred noise. Now, of course, we can't calculate the noise voltage itself, but we calculate the spectral density. So, Svn in, the spectral density of the input referred noise, is Svo, the spectral density of the output noise, divided by GMR squared. Okay. So, what do we get if we do that? That will be equal to 8/3 kT divided by Gm plus 4 kTr divided by GMR squared. Okay. Now, what this means is, in a noiseless version of the circuit, I will just put a star next to it to denote that it is noiseless. Okay. This resistance and this Mosfet do not have any noise. I can represent the noise by the input referred noise like this one. Okay. And this will have a spectral density equal to that. And if you observe here, the first term is nothing but the input referred noise of the Mosfet, the noise of the Mosfet referred to the gate source voltage. Okay. Right. So, if we had used the alternative model of the Mosfet, if we use the model where I have 8/3 kT divided by Gm, okay, and let us say the resistor's noise is modeled by this INR, which has a spectral density of 4 kT divided by R. Okay. So, let us say I use this, then it would be immediately clear that the input referred noise will be 8/3 kT Gm plus something. Okay. That is because this appears at the input of the Mosfet. So, that is why it is many times beneficial to model the noise of the Mosfet as an input referred noise referred to the VGS instead of the output. And if you look at this other term, what do we have? I can rewrite it as 4 kT divided by R divided by Gm square. Okay. Now, what is 4 kT divided by R? That is the spectral density of the noise current that is added here, and the transfer function from the input to the drain current is Gm. Okay. So, the current that is added here divided by Gm square will get added to the input. Okay. So, in general it is true that if you have a number of amplifiers, the noise added at the output of something will get divided by the square of the gain when referred to the input. In this case, the noise current added by the resistor is divided by the gain, where gain refers to the gain from the input voltage to the drain current, the square of that, and get added to the input. Okay. So, by modeling the noise in different ways, there are many cases where we can simply write down the noise spectral density by inspection. First, we can write this down. So, the input referred noise spectral density is 1/3 kT divided by Gm plus the noise added by the resistor, which is having a spectral density of 4 kT by R, divided by the gain of the Mosfet from VGS to the output current, which is Gm square. Okay. So, this is an alternative way of calculation. Now, you can calculate the noise in any which way you want, as long as you get the right results. In fact, initially I suggest that you do it in both ways. You calculate the output noise by proper calculation, and you also try to do it by inspection just for practice, and make sure that the two match. And after enough practice, there will be many circuits for which you will be able to simply look at the circuit and write down the expression for the input noise. Okay. Thank you. I will see you in the next lecture.